All right, so I have a frictionless track that has a ramp on it that is angled theta that leads to a landing at the top of the ramp. I have a small mass that is not connected, that is able to be pushed by a spring. I would like you to come up with an expression for the minimum distance you would have to pull the spring back to get the box up to the landing. Your answer can have d, theta, k, m, and any fundamental constants in it. But again, what I'm looking for is the minimum distance, an expression for the minimum distance that I would have to pull the box back against the spring in order to get the box to the top of the landing. So the top of the landing is here, state 2 of the problem. You can have d, theta, m, k, and any fundamental constants in your answer. Please try this. But we are a little behind, so I hate my glasses. So I think that you all realize there are 2 possible states of the problem. Now, you might think that there are more, and there's lots more. I could consider the time when it's on this surface, zoom in towards the incline. That's a state. There's a time when it's halfway up the incline too, still moving towards the top. You can pick any position you want here and consider that a state of the problem. So don't for a moment think that there's only 2 places. Any 2 places can be compared. The next thing, and this is something that's going to be missed by some of you, we said that there are 2 states, and you're comparing the 2 states. At state 1, the energy appears to be all elastic. I hope you guys all have that. That's 1/2 k x squared. At the other state, what are the possibilities? Well, there's gravitational potential energy, mgd, where d represents the height above the reference level. The lowest point in the problem is the point where it's here, where the mass is. It's going to be up here on the landing. So the change in height is d. That's the symbol I'm supposed to use. You leave it in terms of h, you're not going to get credit. And many of you have been in a test where that's been the case. You've used the letter that was given to you in the equation and left it that way and said, well, can I leave it in h and still get credit? No. They purposely changed these on purpose to see if you know where that's supposed to go. They also are doing that because they're likely to leave distractors in there that you may not need to answer parts of the question. The angle is never necessary. Doesn't matter whether this is a shallow angle or a steep angle. All that matters is the change in the height. But the last thing is the possibility that it could still be moving when it's up there. There could be some kinetic energy, which 1/2 mv squared. Now, I skipped over this part yesterday, and I want to make sure I emphasize it today. We don't actually know if these 2 things are equal. A conservation of energy problem isn't supposed to be so clear-cut. We made it clear-cut yesterday, saying that the way we use conservation of energy is to take 2 points in a problem, equalize their energy, and then solve for some unknown variable. And those unknown variables tend to be things like this. How fast is it going? How high does it go? Or how far back against a spring does it go? That tends to be the outcome of these problems. We tend to never actually calculate the amount of energy. But I want you to also understand that we don't actually know if they're equal. That's the whole point of conservation of energy, is for you to judge whether there has been anything done to the system that might have changed the energy of the system. If there has been, they're not equal. So words like frictionless are things that you can probably use as evidence of why we can set the 2 sets equal to each other. But remember, on an AP exam, I'm often going to ask you to explain yourself. How do you know that the energy at state 1 is equal to the energy at state 2? And your explanation should be about whether work was done on the system by some external force. You should be looking for signs of air resistance, drag, or some other factor that is outside the problem that applies a force to the problem. Normally, it won't be subtle, but the way they're going to do it isn't like this. They're going to say something like, the object doesn't actually make it to the top of the rise. What probably happened? And they're going to ask for a conjecture from you. That's where you'll have to say, well, either the spring didn't actually have the amount of energy in it that we thought. That's a possibility. There was friction on the track that we weren't aware of. That's a possibility. Another possibility, of course, is perhaps the thing was higher than we anticipated. That's also a possibility. Perhaps the whole thing wasn't on a level surface. That's a possibility. They're going to be looking for you to make a conjecture about what could have prevented the object from doing what we thought it was going to do. So they're not going to just say, are they equal? That's a little too pedestrian. Now, once we've established that these are equal, or we feel confident, you have to take this into account. Minimum. What does the minimum mean? It has to get to the landing. It doesn't have to be moving when it makes it up to the landing. It can get right up there and be stopped. So when we talk about minimums, you have to know what part of the energy can be sacrificed and forced in favor of something else. So that gives us the 1/2 kx squared equals mgd. And you can solve for x min as being the square root of mgd over k. And it is here where you should look at how these variables are related. If I want to go to a higher location, well, I'm going to have to make the minimum more. If I want to use a different spring, well, that's going to impact how I have to deal with the minimum. Pretty straightforward so far? Not a problem? Or is this a problem? You need another practice? Well, we're going to do like 4. But what I want to do is I want to talk to you about when we have a track like this where the box is going to hit a patch that has friction. Is this a conservation of energy problem? Well, it really depends on how you view conservation of energy. See, to me, this one's pretty simple, clear cut. I could probably compare state 1 and state 2 pretty easily. State 1, there's going to be elastic potential energy. State 2, there's going to be kinetic energy. I think that when the object is shooting along this frictionless surface, it's going to have some velocity. And that kinetic energy was given to it by the spring. I think we could probably set these two things equal to each other because there was nothing that did work on the system between those two. Does that make sense? But is the energy at state A equal to the energy at state B? Is there an external force that does work on the system between A and B? The answer is yes, and these aren't equal. The amount of energy isn't equal. Now, we have a method for talking about that. We've already done this. If there was work done by friction, then that's going to have to equal the change in kinetic energy. This is the problem we've done before. And in doing that problem, I'll remind you, we would say, okay, work equals force times distance times the cosine of the angle. That's going to be, let's see, the box when it's in the section where the friction is, it's going to have a downward force of weight, an upwards normal force, and a frictional force. Can you think of any other forces acting on the box as it's sliding across that section? I can't. I just want to make sure we all are in the same boat here. So the box is going to be going in this direction. That's its velocity. But the frictional force is acting to the left. So I would say the work done would be friction times the displacement times the cosine of 180 degrees. Because the frictional force is to the left, but the box is moving to the right. We've done this problem before. And then, of course, we'd have to figure out what the friction is. Yet another problem we've done before. We'd probably remember that friction is equal to mu times the normal force. Normal force is equal to mg. I know writing all this down is what I'm supposed to do, but I think we've also reached a point where I can say that friction is just mu mg d and put the negative sign out there because of the cosine of 180. Well, this has to equal the change in kinetic energy. Now, I'm not surprised by this. In this particular example, I expect the kinetic energy to be less because friction took some of the energy away. Does that make sense? Any question about this? We've done this problem. I feel like I'm not really changing this very much. Now, this represents the work done by friction, and it is negative. Now, I'm bringing this up because, well, if we look at A and B, I don't know where I'm going to put this, so let me try this. If we look at A and B, there is kinetic energy at A. I'd call this the initial kinetic energy, or if you'd like, the kinetic energy at A. Because there's also going to be kinetic energy at B. And I don't think they're going to be the same, because at B, we know some of the energy was left on the table. If we take this right here, this thing that we just kind of developed using the work energy theorem, this has to be equal to mgd K final minus K initial. That's what that has to be. Now, just follow me for just a minute. I'm not trying to make this hard, but let's add this to both sides. I'll get Ka minus mu mgd equals Kb. Now, here's the thing. If we think all energy is conserved, if that's something that you like, that is in your mindset, then you could say that Ka minus the work done by friction has to equal Kb, and say that this is a conservation of energy problem. Now, I don't like it this way. I would have said that because all energies are supposed to be positive, you should write it like this. There's the amount of energy we have at A, and this represents the amount of energy in the system at B. Some of it is spread out all over this pad, right? It's hot now because there was friction there, made noise or something. But I'm equating one amount of energy with another amount of energy. I'm bringing this up because I've been teaching for 26 years. And in 26 years, one way we were supposed to teach conservation of energy is that you subtract the work done by friction on the side before the work is done. And then I was told that we have to teach it so that we keep track of the energy and make all energies positive. So we say that there's the energy before, it has to equal the energy after, but you make all your energies positive. So if there's work done in the interim, you put it like that. I've also been around long enough to see that there's times you're supposed to say, well, Ka equals Kb, but we put the work on top of the equal sign so that the kids know that something happened across the interim, and they have to keep in their mind whether the work was positive or negative. And then there's what your book does, which is they make it so much more eloquent by having a set of bar graphs to really drive home pictorially that there was kinetic energy here, there was negative work done, and now there's new kinetic energy here. Right, you saw the bar graph stuff in the book, where this represents the equal sign and work sits in the middle between one set of energies and the other set of energies. Now, do you realize that none of this is any different? It's all the same thing, just a different way of holding it in your head. The way I tend to think about it tends to be this one. I tend to think, all right, when we were traveling in such a way that the cart had energy when it was here, if I'm trying to keep track of where the energy went, By the time the cart made it to here, it had left energy all along the ground between them, but it still had some energy here. I like making energies positive. I think if everything's supposed to be positive, I don't ever have to work that much. I just need to know that the energy was taken away from the car during the time it was on the pad, and the energy still exists. It's just now on the pad because it got hotter. That's how I tend to think of it. The energy's still there, but the energy now exists as heat on the pad. That way, when you look at this, you say, okay, they're actually equal if you include the amount of heat that was left on the pad. That tends to be the way I think about it. What I want you to understand is that it doesn't really matter which way I teach you. They're all going to work out the same. You could do what we did last week and realize that, okay, when we hit the pad, work is done by friction. It's going to change the kinetic energy. That works just fine. And you'll be okay. You can say, well, I have to subtract the thing that took away energy. And then whatever's left over is what it has when it's done. That's this way. Or you could do what I kind of think, is that this is the energy it had before it hit the pad. This is all the energy that's still in the system after it passes the pad. They all are the same. They come from the same place. But here's why I want you to be thoughtful about this or mindful about this. So, I mean, consider this problem. Any place that's yellow, no friction. Blue has friction. Okay? So there's a coefficient of friction along the inclined portion of this problem. Now, can we agree the box is going to have at state 1 a certain amount of energy when it's pulled back against the spring? It's going to have a certain amount of energy at state 2. It's going to have a certain amount of energy at state 3. I'm bringing this up because potentially at state 1, probably elastic potential energy makes the most sense. State 2, kinetic energy makes the most sense. State 3, well, it's up high, so gravitational potential energy. And it might still be moving, don't really know. But we know that it lost energy here. That makes the work energy theorem kind of hard to deal with. Because the work energy theorem might have taken away some kinetic energy, but some of the energy was also converted into gravitational potential energy. That makes this method harder to do. Because how much of it was energy taken away from kinetic and how much of it was energy that was put into gravitational potential? Because it's moving up the whole time. So there's work being done by many forces there. There's work being done by gravity. There's work being done by the frictional force. There's work being done by the normal force. They are all messing around with it. So I tend to like the idea that we say, okay, between state 2 and state 3, if I want to make the energies equal, then I say, well, at state 2, there was kinetic. At state 3, there's gravitational and potentially some kinetic. But also, while it slid up the ramp got hotter, and it has some of the energy too. What is this going to do? This is going to make the object probably slower, right? It has to have a certain amount of energy to make it to the top. It can't take the energy away from the gravitational potential because otherwise it doesn't make it to the top. But probably when it makes it up there, it's probably traveling at a slower speed. Why? Some of that energy went here. I like this one. I like teaching this method. I think this method makes me say that all the energies are accounted for. That I started with this much, I still have this much energy. It's just that some of it I'm not getting back. It's stuck all over the track. The track got hotter. That's not going to make the car move any faster or slower. Now, AP is not going to actually have you calculate the energy here in the way that you're thinking. It's not going to say, all right, draw a free body diagram and do all the work necessary. They're not going to do that. You don't have time, really, on the exam. But more importantly, that's not really what this class is about. So to understand how AP is, or day before yesterday, I want to start with something that's easy that I know you guys can do. Bear with me. Nope, don't like it. There. That's going to have to do. Let's say this is 2 meters high. And we'll say that the track for right now is frictionless. And you put a box on the track. So there's our box, mass M, just chilling on the track, okay? You release the box from rest. How fast is the box going at 0.2? The expectation is this takes you like 60 seconds. Use 10 for G. We really don't think this should take that long. We're talking all gravitational potential energy here, released from rest, top of the ramp. Down here, kinetic energy. 1/2 mv squared equals mgd. I don't know why I put them on opposite sides. I shouldn't have done that. There, all better. So square root of 40, right? 6.3. All right, so you build this contraption. I have it sitting right over there, the whole loop-de-loop thing. You build this contraption, you put the car at the top, you release it, and when you actually do the work, you find the velocity is only 5 meters per second. It's supposed to be 6.3, it's only 5. Why is it only 5? What likely is an untrue statement about this whole problem? Yeah, it's not frictionless. Can you figure out how much work was done by friction? You could calculate this. You could figure it out. To do that, you'll need to know the mass of the car, though. To actually get the work done by friction, you need the mass of the car. Let's keep going with let's say it's 1 kilogram. Nice and easy. So I know the work done by friction. Now I'm hoping that I'm not asking a whole lot, that, all right, we kind of now know what this final velocity is. It's not unknown, it's 5. And these things are not equal now. Well, that means that there had to have been some work done by friction. The track got hotter during the course of this. If I want them to equalize, I need to account for the energy that was lost due to friction. It doesn't matter that the track is circular at a weird angle. I can't calculate the work done by using a force and distance and an angle. That's all weird there because it's at a circle and angles and curvy stuff. I don't need that. I know how much energy I'm supposed to have. I know how much energy I ended up with. Whatever's missing, that had to be the work done by friction or air resistance or something else. Doesn't really matter what. So we get 20 on this side, and I get 1/2 of 25 on this side, plus work done by friction. You find the work done by friction is what, 7.5? Not terrible? All right. That's not an AP question. Here's the AP question. Here's how AP is going to do this. AP is going to give you the same track. They are not going to tell you how high it is. They're not going to tell you the mass. They're going to say that this track is set up on a table. and that you do your measurements and you predict that the box is going to land here, a distance d away. They're going to then ask you questions like, what if you started the box here? Will the box land before D or after D? Now, you should be able to figure that out. I hope you realize if you start the box here, will it be going faster or slower here? Why? Can you explain it? I'm saying this because, remember, you have to be able to explain yourself. Can you say, if I start the box lower, it will have less gravitational potential energy? And if it has less gravitational potential energy, it will have less kinetic energy. Can you say those things? Because that's what you're going to have to do. Now, here's the thing that you guys tend to have trouble with on these tests. You'll say it has less kinetic energy, therefore it will land over here. That's not enough. You're making me decide whether you know kinetic energy means less velocity. You can't make me make that decision. You have to also say that less kinetic energy means it's traveling slower. If it's traveling slower, it won't travel as far sideways. Do you understand the difference there? You have to explain every little piece. You have to connect it all together. So you can't make an assumption that the person reading your work knows physics. You have to explain all the details to them. The same kind of problem can be set up here. Not ask about this, but say that you predict the object's supposed to land at D, but it lands in the area of number 1. What was likely wrong? You have to say, well, some energy was probably taken away from the box. Probably there was some friction on the track or air resistance acted on the track. If it's a spring launcher, it could be any number of things, like the spring constant wasn't the same, or you didn't pull it back as far as you thought you did. These are the kinds of things that you have to place in your problem. And understanding that it's not going to be always about calculating something. Sometimes it's going to be about you making an inference about how changing one thing in your problem affects all of the other things. I told you this kind of at the beginning of the year that your problems are not going to be about one thing. They're going to try and mix all the things up. I hope all of you realize no matter where you start the car, let me say that again, no matter where you start the car, no matter how much friction there is, it takes the same amount of time for every box to hit the floor, right? The desk is the same height all the time. The time in the air depends on how tall the desk is. Does that ever change whether you start the box here or start the box here? The answer would be no, because that has nothing to do with it. But the velocity here determines how far away the box lands. Those are the kinds of questions they're going to ask. That's what I'm going to be asking you tomorrow. There'll probably be a portion where you'll have to calculate something or come up with an expression. And then there's going to be a follow-up where we're going to ask about what if this was the case. And you'll have to be able to explain it from beginning to end. So I like the idea that you can compare two states of a problem and question whether they're equal. And if energy was taken away by some other force, that you place that energy as work done during the transition from this state to this state. That's how I like it done. All right. Believe we're at the end of class. Is there any follow-up questions or anything from the homework still bugging you? All right, we're done for the day.